Hello dear students, the lecture today is about trigonometric function transformations. In particular, we are going to see stretches on the vertical axis or compressions, as well horizontal. We will additionally see horizontal shifts to the right or to the left. In order to understand these transformations, you need to realize that they are a consequence of the composition of two distinct types of functions, in particular trigonometric functions and polynomials of degree 1. So let's start with the first example and consider the transformation from the old sine of theta that we studied last lecture into sine of theta times a constant. It could be any constant that you choose, okay? Just multiply. What are the functions involved in this composition? By looking at it, we realize that we have f of theta, the trigonometric function, which is the sine. We also have the polynomial g of x, which is the constant times x. Recall what is the general formula for a polynomial of degree 1. P1 of x in general is ax plus b. A and b are parameters, that is, numbers that you choose. X is the input, a gives you the slope of this line, and b the y-axis intersection. In this case, b is 0 and a is a constant that you choose. With these two functions, we can now make the following composition. First, let's look at it. First, you act with sine on theta, so we have the first is f, and then you act on f with the function g. So g of f as applied to the variable theta gives you, well, you just put f here at the x, so you have the constant times the sine. Okay? Well, I don't want to carry this constant around, so let's rename it in something easier to write, like a. A for amplitude, a number that you choose. It's easier to work with a. Okay? Now, our goal now is to draw the graph of this thing. You see? Here's the idea. We already know how the transformation happens analytically. Before you have this, now you have this. But what about the graph? Well, how does the graph of this compares with the graph of this? You have to make the graph of this function. This is our goal, and to compare the two. So we saw last lecture how to do the graphs for these types of functions. We do like police investigators do. You look at the hackers, the criminals, you gather as much information as you can about them, and then you piece together, use this information to understand what they do graphically. Okay? And this is what we are going to do first for the sine, and then let's focus on this. So for the case of the sine, from last lecture, I'll report as the following information. First, the sine, periodicity. What's the periodicity of that function? Well, if you have sine applied to an angle theta, and you add a full perimeter of the unit circle, that is 2 pi, then the number that you get here is the same as sine of theta. Okay? But whether you add a full perimeter or subtract, or add a multiple of that perimeter, is the same. So instead of 2 pi, we should write n times 2 pi, where n is an integer, positive or negative. Okay? So you add anything and you get this. This is the conclusion for this function. What about the maximum and minimum of that function? And zeros. What are the max, min, and zeros? Well, recall that sine of pi over 2 is the maximum value of sine, which is 1. Sine of 3 pi divided by 2 is minus 1, the smallest one. And the zeros, let's see the picture. Recall the unit circle. The sine lives on the vertical axis, so pi over 2 is this angle, the measurement of this arc. It's pi over 2. Well, the y-coordinate of this point is 1, so the sine of pi over 2 is 1. The arc that measures 3 pi divided by 2 radians starts here, goes around, and ends here. And this point here has y-coordinate minus 1. The zeros occur when theta is 0 or when theta is pi. Okay? Of course, we have to add full rotations because it could be pi plus 2 pi and so on. But for now, let's just focus on these cases. Okay? Let's move on. What other property about the sine did we saw last lecture? Well, it was the symmetry, antisymmetry in this case. The symmetry says that the sine of a negative angle is the negative of the sine of the positive angle. Or in other words, whatever happens on the positive theta axis, the positive side, times minus 1 is what happens at the negative side of the theta axis. Okay? So this is the information that we got from last lecture. And from it, we can now draw the graph of the sine. How do we proceed to draw the graph of this function? We start by drawing the axis. This is the theta axis. We start by marking the easiest points, the important points, the easiest ones. These points, for example, pi over 2 and 3 pi over 2 and the zeros. Well, let's mark it 2 pi. 1/2 is pi. 1/2 is pi over 2. Pi plus pi over 2 is 3 pi divided by 2. And this is 0. And now let's mark the points. Sine of pi over 2 is 1. So this is the first image, 1. So this height from here to here is 1. To the point pi over 2 is associated this height. Here is minus 1, right? So let's mark it minus 1 here. So to the point 3 pi divided by 2, we associate this negative height. Okay? Minus 1. Now let's go to the zeros. At 0, sine of 0 is 0. So the image is 0. Sine of pi is 0. What about the sine of 2 pi? Right? We use the periodicity, right? Because if you choose theta 0, here, you have sine of 0 plus n2 pi is equal to sine of 0, right? But sine of 0 is 0. So sine of 2 pi, 2n2 pi is 0 all the time. Well, for the smallest period, that is when n is equal to 1, you have sine of 2 pi. So sine of 2 pi must be 0 as well. Notice the period, the smallest period 2 pi, is this distance, right? So the function needs to repeat itself from here to here, right? These points must be the same value, okay? Now that we have drawn the important points, we draw what happens in between, here, 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 and here. And so, we saw last lecture this in detail. The function sine don't do something crazy between these 2 points, or these points. It just increases. It increases, it bends, it reaches a maximum of 1, and it decreases, reaches 0, keeps on decreasing, reaches minus 1, and then decreases. Okay? To 0 again. Here is the wave. Okay? Now, to complete the graph, we need to draw the negative side of the theta axis. So first, mark these points. Minus pi over 2, minus pi, minus 3 pi over 2, and finally, minus 2 pi. You repeat the procedure, but now we use the symmetry property, right? Because if theta is pi over 2, here we have minus pi over 2. So sine of minus pi over 2 is minus sine of pi over 2, right? So here, sine of this value is 1. Sine of this value must be minus this value. So this is the height of this point is negative. Here. Here, the sine of this point is a negative of the sine of this point. But this is 0. So minus 1 times 0 is 0. So this is 0 again. We proceed. the sine of this point is minus the sine of this point. So this height is negative, times minus 1 becomes positive, so this is 1. Here it is. Finally, we start by 2 pi, right? Is 0, so this is 0 again. And now we use this property again to fill the intermediate points here, 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 and here. So this is, if this is positive here, here it must be negative. Okay? If this is negative, here it must be positive. Okay? And this is the sine wave. Okay? The sine wave from minus pi to 2 pi. Okay? So our first goal is done. We already know how this thing behaves. Okay? We use the data to draw this picture. Now let's proceed and do the same for this function. Okay, so this is a second report, the periodicity. Periodicity. What's the periodicity of this new function, right? The new function, let me write it again, is g of f of theta, which is a times sine of theta. Okay? The constant is called a. To get the periodicity, notice that if I multiply this by a, okay, if this is true, okay, and we know this is true, let's multiply by a on both sides, and we get a sine theta plus n to pi equals a sine theta. This formula, if this formula is true, this formula is true. But what does this formula say? It says that the period of the new function must be n to pi. So this doesn't change. So the transformation, if you just multiply the sine by the constant, the period doesn't change. What about the max and minimum? Again, if this is true, sine pi over 2 is equal to 1. Well, let's multiply by a. Sine a times sine pi over 2. Well, sine pi over 2 is 1, so this is the same as a. A sine 3 pi divided by 2. Sine 3 pi over 2 is minus 1, so this is minus a. Okay? But what about the zeros? Notice, this function here, only this part depends on theta. The constant doesn't. So this function, when it's maximum when this is maximum. This is minimum when this is minimum. And this is 0 when this is 0. And so the zeros of the old function are the same as the zeros of this function. Okay? What about the symmetry? Symmetry. Well, you just multiply by a. It's the same. This is still antisymmetric, right? Is equal to a sine of theta. Minus, by the way. It has a minus sign. Okay? So this function is antisymmetric again. Okay? What happens on the positive side of the theta axis times minus 1 is what happens on the other side. Okay? So this is the data that we are able to collect about this hacker, the criminal. And now we are going to use it to make the picture. We start by drawing the easiest points, the important points here. What's the maximum, minimum, zeros? Okay, let's start. But let's consider a equals to 1.3. So this is 1.3. To make it easier, let's mark it 1.3 here, here, minus 1.3. Here it is. Like this. And like this. These guidelines then will be useful, right? So 1.3, the maximum, now it's 1.3. So this is definitely on one of the points. At pi over 2, we associate this height. To 3 pi over 2, we associate this height that goes up to here, right? Minus 1.3. The zeros are the same. So this sine of a sine of 0 is 0. A sine of pi is 0, and a sine of 2 pi is 0 again. And now, what's missing now? Let's fill in the intermediate points, from this point to this, from this to this, and so on, right? But how do we proceed, right? Because let's analyze the function. You see, is the sine I'm sorry. So the sine is this blue curve, and you are multiplying every height, each one of these heights, these and these and these and these, by 1.3. It's a number larger than 1, so these heights must increase. So that means that, well, the function is 0 at 0, but just a bit later, it must be above, because you have this line, and you have to increase it by multiplying by 1.3. So the function is always above the blue curve, like this, and it only intersects the blue curve at the zeros. Here, the outputs, or the images of these points, are these lines, and they are negative, but if you multiply by a number larger than 1, like this, then they get even more negative. So they have to be below the blue curve, like this. It reaches the minimum here at 1.3, minus 1.3, and then it decreases again and intersects the blue curve only at the 0. Okay? This is good. Now, we are using the information that we have. Notice that we not only know this, you also know this. So you have to use all the information that you have so that you fill the details. So the transform function behaves in a similar way. Okay? Let's now proceed and copy. Use this anti-symmetry property and copy here, right? This is minus 1. I'm sorry, minus 1.3. This is 1.3. The zeros remain the same, right? And just fill in the gaps. If this behaves like this, here it behaves like this. If here behaves like this, multiply by minus 1, here behaves like this. Okay? Can you see? Notice that the function, the transform function, is stretched with respect to this one. You see? When you multiply the old function, the sine, by a number larger than 1, you stretch the thing. Okay? What about if a... What if a is between 0 and 1? Let's put in green. What if a is smaller than 1, but still positive? Well, we can immediately see the maximum, which is 1 on the blue curve, is multiplied by minus 1. I'm sorry, multiplied by a, which is smaller than 1, and so it gets smaller, right? So in all the points, these bars become smaller, like this, or like this. And here you just copy, using the anti-symmetry property. Okay? There is only intersection at the zeros. All the time the function is below the blue function, okay? Lastly, what if a now is negative? So a is smaller than 0. What happens if a is smaller than 0? Let's see. Let's put in red color. So a is smaller than 0. You see? If a is smaller than 0, then that means that a can be written as its positive part times minus 1. And so, when I say a sine of theta, and a is negative, then that's the same thing as saying minus 1 times the absolute value of a times sine of theta. Okay? But if the absolute value of a is in this case between 0 and 1, or is just larger than 1. So this part here, we already know how to do, right? You either in the case of one of these curves, right? The green, the black, or the blue. Okay? So this is nothing new to draw this part. So the only thing that's new is what the effect is of multiplying these by minus 1. But this is easy, because any output of this thing, any value that it takes, is just flip the sign. So in this case, let's take the blue curve, the original sign here, when the original sign, if you multiply it by minus 1, well, here the outputs are positive, well, you make them negative, right? Like this. This is the minimum, no, minus 1. And here, 1, this is the maximum, right? It does like this, right? Here it's the opposite. And let's me does like this, okay? It just flipped, right? It just flipped through the theta axis. Okay? Now, this is all good. Now let's proceed. Let's proceed to another kind of transformation. Okay? Another kind of transformation is, you see, let me erase this. The next kind of transformation, you see, on this one we multiply the outputs by the constant. But on this transformation will be different. We are going to multiply the arguments, the theta, by the constant. So instead of this, we consider the sine. You consider the sine of the constant times x. X is the input, the number that you have to choose. The constant is the number that you choose. So f and g are still the functions involved in this composition, just like we had in the previous case. On the previous case, we considered g of f. That's why we had the constant a times sine. But now it's different. We consider the opposite direction, f of g. Now, as a function of f, x, and this is the sine. You see, you just put this here. Let's call the constant times x, right? Notice, maybe it's important to notice, this theta became this constant, the constant times x. This is theta. The whole theta became this, okay? So you put this here, okay? The composition. Well, I don't want to carry this constant around, and I'm going to give it a special name. Not a, because a is reserved for the amplitude. Let's call it k. Here is k. Okay? And let's erase this because this is from the previous example. Our goal now is to study this kind of transformation from the sine up to here. Okay? Well, we already know how to proceed for the case of the sine. Now let's gather information for the case of this function. So let's erase this and do the same analysis to gather information about this new criminal. Okay? So let's start by the maximum minimum. Where the maximum minimum, see, this is still a sine, so the maximum minimum are still 1 and minus 1. But the position on the horizontal axis is different. Why? Because we messed with the inputs by multiplying by k. So the position on the horizontal axis is different. So let's see where on the horizontal axis is that 1 or minus 1. Okay? We proceed as follows. We are going to try to compute sine of k times x max, where x max is a name that I chose for a very special value of x. It's special because it's the x you have to choose, so that when you apply sine to kx max, it gives the maximum value, that is 1. Similarly, let's call kx min, and kx min is a special name that I give to a special value. I don't know what it is, but I give it already a special name. It's a special name so that when you apply sine kx min, it has to give minus 1, and that's it. And the same for the zeros. Sine kx0, x0 is a name that I gave, so that this calculation must give 0. So the only unknowns is x max, x min, and x0, where k is chosen by you. Okay? Now let's solve this. Let's solve this. How do we solve this? You solve this by comparing this with this. And comparing the first one with this, we realize that this part here must be pi over 2. Let me write kx max, write it here. Kx max must be pi divided by 2. Compare this with this, and you know that kx min must be 3 pi divided by 2. And finally compare this with either 0 or pi, and you know that kx0 must be 0 or kx0 must be pi. Now we solve this thing, right? Just rearrange, divide by k on both sides, and you have pi divided by 2k, divided by those sides, 3 pi divided by 2k, divided by those sides, x0 is 0, and divided by two sides, it's pi divided by k. Okay? This is very important result because it gives you the positions where the 1 is above this point, -1 is above this point, and zeros are located along the horizontal axis at these coordinates. Okay? Very important result. What about the symmetry? Let's consider symmetry now. You see? Because theta became kx, kx is just an angle. Okay? It's just another symbol for the angle. So the symmetry is kept. So sine of minus kx must be minus sine kx. It's still antisymmetric. Okay? What about the period? Let's do the calculation for the period. The definition is the period is always useful instead of thinking about the formulas, think about the idea. What's the period? The period is a number that you need to add. It's a number that you need to add to the argument. So the number that I need to add to x, let's call it lambda, so that this thing remains the same. So sine kx. So adding this lambda number, lambda is a Greek letter, it's a period. If you add lambda to x, well, it doesn't change the calculation. It's still sine kx. Okay, but sine k times x plus lambda is the same thing as sine kx plus k lambda. And so let's compare this equation with this equation. Kx is theta, kx is theta, and so k lambda must be n to pi. So let's write this. K lambda must be n to pi. And you now can see that the period can be computed from n to pi and k, the number that it shows. So we write it like this. There are many lambdas, many periods, okay, for each one of these n's. The smallest of which occurs when n is equal to 1. When n is 1, lambda is 2 pi divided by k. Okay? Let's underline this thing because it's another important result from here. Now that we have all this information, we are ready to make the graph for this and compare what's the consequences of this transformation. Okay? Let me draw it. Here it is. From here to here is 2 pi, then it's just pi, and then it's pi over 2, and this is 3 pi divided by 2. Okay? Let's mark the points. This is 1. Here it's -1. Here the maximum is 1. I'm drawing first a sign, then it's 0, then it's -1, and then it's 0. This is 0, and so it does like this. Okay? Here it is minus pi over 2, minus pi, minus 3 pi divided by 2, and finally minus 2 pi. Mark the points. So this must be -1 because this is 1. This is 0 because this is 0. If this is -1, this is 1. And finally 0, 0. It's antisymmetric. Now just repeat this. Fill in the intermediate values, and we have the sign, the graph of this. Okay? Now let's proceed and draw the graph for this, for the transformed function. We start by drawing the important points, and the important points is where are the maximum, minimum, and zeros. So let's start. You know that x max, okay, let's start with choosing k first. Let's consider k equals 2, okay? If k is equal to 2, then the x max is at pi divided by 4. So pi divided by 4 is pi over 2 divided by 2, right? It's here. Pi divided by 4. And that this value, the height above it, must be 1. Here's the point. The image, the height, is 1. The x-mean is at 3 pi divided by 4. 3 pi divided by 4 is here. 3 pi divided by 4. Okay? And the value of which is minus 1. This is not very straight. Okay. This should be here. Like this. Okay. Now it's good. So the height of this thing, go from here to here, is minus 1. So this is good. This is good. Now let's see. 0 is 0. It's the image of 0 is 0. The image of another 0 at pi divided by 2. So at pi divided by 2, we have the 0 again. Okay? And let's see the period. What is the period? The period is pi, right? Because k is 2, you get n times 2 pi divided by 2, so n pi, but the smallest period appears when n is 1, so lambda is pi. So from here to here, right? Because from here to here you have pi, then the graph here must be the same value as here, because the period tells when the values, the outputs or the images repeat again. So this must be 0. From pi over 4 until this point in the middle, which is pi plus pi over 4, the image must be again 1, because again this distance from here to here is pi, the period, the smallest one. Again, let's repeat. Pi over 2 plus pi is 3 pi divided by 2. And so this value, if it's 0 here, is 0 here. And we proceed. Another pi. 3 pi divided by 4 plus pi is here, in the middle between this point and this point. And the value is minus 1. And finally, pi plus pi is 2 pi. And this value is again 0, like this one was. Now that we have some of the important points, let's do the intermediate. The intermediate, you get inspired. You get inspired on the blue curve, you see? So it must increase up to 1 here, and then decrease. It keeps on decreasing, and then decreases again. It goes up, and goes down, and then again up. Right? Now what's left, you just copy this thing to the other side. Okay? And so this is minus 1. So this is, if this is 1, this is minus 1. This is 0, this is 0, right? The anti-symmetry property enters in the game. And then at minus pi, it is 0, this is 0, right? There is one point missing. At this point, 3 pi divided by 4, at minus 3 pi divided by 4, it's minus 1. Now this is 1. This intermediate point is 1, right? And finally, here, between minus 3 pi divided by 2 and minus pi, leaves another minus 1. And at 3 pi over 2, it's 0. And at 2 pi, in between minus 2 pi and minus 3 pi over 2 leaves this point, but positive. And finally, you get 0 again. And so you fill the gaps like this, and like this, like this, and it decreases. I'm sorry, this is very... Okay. What do we see? What do we see about this? It's compressed, right? If k is larger than 1, the function got compressed. The transform function is compressed with respect to the other one. Okay? Let me just stress here a point, a very important point, because it might not be obvious to you immediately. Let's do step by step. We started by drawing the sine of theta, right? In this graph, the blue curve. But notice, the sine of theta is a function of theta. And so the horizontal axis is theta, in fact. This is the first point you need to understand. The second point you need to understand. The transformed function is a function of x, not of theta. It's x. So I would need another axis. I'm sorry, this is empty. I would need another axis. This is good. Another axis. Call it x. This is 0. And then from this axis, the x-axis, draw then the function. Okay? The green one. What you see here is a superposition of these two graphs, where I just bring this x-axis up to here, and now you have two axes superimposed, the theta one and the x one. Now, when do we consider theta, or when do we talk about theta or x? Well, it depends upon whether we are talking about the the blue curve, which uses theta, or the green one, which uses x. Let's put x in green. Okay? So there are two graphs superimposed, like this. If it's not clear, it's theta, sine theta, and x, and sine kx. You superimpose these two things, this is what you see here. Notice that the values of x and theta coincide. Okay, I'm making that choice. So when I talk about pi over 4, well, it's theta pi over 4 or x pi over 4, and then you compare the two images. Okay, this is an important point. Okay, now what happens? You see the period. I forgot the period. Before I move on to the other case, the period here. This is lambda, right? Which is pi, right? From here to here is pi. From here to here is pi, right? The new period of the new function, the transformed one. What about the period of the sine, the blue one? It's from here to here. So the old period is like this, is 2 pi, right? The smallest period, when n equals 1, is 2 pi. Here it's pi. So you can see when k is 2, you just split this thing into parts. Okay? Now, if k increases, the function compresses. What if k is smaller than 1 now? If k is smaller than 1, it's the case I'll leave you as a homework. This case. Okay? And the negative as well. You can find the details in the notes. Okay? But I think you can work it out. You just derive again. You derive, you just use this consequence because this is valid for either case. And you just put here 1 over 2, for example. It's easier, 1 over 2, 1/2. And you just try to, from this information, and this information, right, and this, to draw the picture and see what happens, okay? I want you to leave this as a homework because I want to focus now on another point of view on this particular kind of transformation, which could be illuminating, okay? Because you see, you multiply by 2, but the thing compresses. You would think the other way, right? If you multiply, you must increase, right? But that's not what happens. So let's look at this from a new point of view. So I will erase this. Because I want to study each of the functions involved in the composition. The functions involved in the composition are here. So it is x is transformed by k times x yields the value kx, the output, and then on this thing you apply the sine. And the number that you get from this is the number of sine kx, the number. Okay? This is the first one. The second one is this, the simple theta. Theta gets transformed by sine into sine theta. This is the procedure that you need to apply. Now, it's like an assembly line. You transform the raw material into a final product. This is a smaller factory, by the way. Now, what do we want to do now? Let's analyze these diagrams. Okay? And try to relate this thing with what you see here. Okay? Now, let's look at each one of these functions at a time. Let's look at this. The polynomial. The polynomial. Let me draw like this. Maybe I want to put it larger, like this. The k was 2, so this is something like this. Right? This is x. This is kx. Okay, and the idea is you choose a point here and you get a result. Okay, if you choose a set of points here, you get a set of points here. Very important. If I choose the following set of points, let's call the set of points A. A is a point between 0 and pi over 2, right? Is this sequence of points here? If you choose the sequence of points between 0 and pi over 2, 0 and pi over 2, then this function, well, it transforms 0 into 0 because k times 0 is 0, and pi over 2, it transforms it into k times pi over 2, but that's just pi, right? Can you see? This line is 2x, by the way. It's 2x, the transforming function. So you transform this thing into this thing. Let me just paint this in red. So this is the final. So you transform the black interval, the interval A, into k times A. Okay? K times A is a set, the set of points that come as a result of multiplying each one of these points in A by k. And k is 2, right? This is the meaning. K is 2. Okay? We transform from here to here. This is what this thing does. Let's now see horizontally how this works. Let me just draw it from another point of view. I need to make this reasonably straight. So this is 0. And our initial interval A is from here to here. Let me just paint it in black. So this is A. And the transformed is twice. From here up to here. Okay? So this is KA and this is A. Above. From here to here. Right? The crucial point, the important point here is to notice this, that this set is increased. Okay? This is a small window, this is a large window. This is a small window, A, and then we increase by a factor of 2. Okay? It becomes twice as much. Or if you choose another k, k times as much. Okay? So the idea is get larger. Now, this is an analysis we can do for this particular case. Okay? Now, let's analyze the second function, which is a sine, or this function, the same. Okay? Let me just draw it. The sine, let's just focus on the positive part of the sine. I don't need anything else. Like this. Okay? Let's exaggerate a little bit. Okay? Let's see what are the images of the set A under this function. Let's use the black again. A is from here to here, right? Can you see? This is A, because the latest value is pi over 2, where it's maximum. Okay? Can you see? Now, the image of A under this function is this set of heights. Can you see? From 0 to 1. This is 1, the maximum. Okay? Is it okay? So this set of values from 1 and 0 here are what's called sine of A. Sine of A is a set of values that come as a result of applying the sine to each one of the points in A. And you get these heights. Okay? So we have sine of A there. Good. Now, you can we just interpret in this figure, we just interpret the meaning of this transformation, of this calculation, of this factory, from this to this, from the raw product, the elements in A, until you get sine of A, right? And you get is this heights from 0 to 1. Good. But because this factory is larger, it first starts with A and first transforms A into Ka and only then evaluate the sine at Ka, this first part. So it starts with A, you get Ka, and then you evaluate the sine on Ka and you get sine Ka. let's see what is sine of Ka. Let's first draw Ka here, because this is a sine. Remember, this is a sine. So we are analyzing the second part. The second part, when the input is Ka. So let's draw Ka here. It starts at 0 and goes until pi. Right? And when we evaluate now the sine for each point in Ka, we get these heights that cover all these things. Okay? Can you see? These bars are like the outputs. You evaluate at this point, at this point, at this point, and so on. Right? Is this good? The set of outputs. Now, what does this say? It says that you associate with A all these numbers, right? Can you see? This is a very important idea. The red, let's see. The red bars here, or the red outputs, are the outputs of the sine applied on Ka. But what this function does, the f of g, right, or the composite function, the entire function, we will associate the red bars not to Ka, but to A, because the input is A. Here is A. Let me draw a picture. This is A. So we associate with A this thing, which is this thing, is going to associate this thing. Like this. Can you see? All these numbers that you get. But notice that A is very small, it's just f of it. So the only way you can now draw this association is to compress the thing. You need to compress like this is rubber. You push it down, right? And you get all the red bars over A. Okay? And as a result, you get this. I'm sorry if you can see this. And you get this. So this is pi here, this is 0, this is pi over 2. Here, let me draw A. And this ink is missing now, but I think we are good. And let me draw in red what I want to say. Like this. Can you see? And then the thing keeps on going. If I were to repeat this for the intervals other than A, that's what happens. So this is a representation, a graphical representation, of the association of the values between 0 and pi, that is a set A, gets transformed into the red bars, which is the outcomes or the results of this procedure. Okay? Okay? The first point of A is associated with 0, the last one with 0 again, and the middle, pi over 4, will be associated with the maximum. Okay? Can you see this? I hope this is clear. Okay? This is the graphical, the reason why this is compressed, because you are first changing from a small window into a large window, right? The large window, which is Ka, or 2a, right? In the case of when k is 2, and then you evaluate the sign on this, but because this is very large, you get many values, and now you have to compress them so that can fit here, right? And that's what you see here. Okay? Each one of the points in A must be associated with one of these red bars. That's the idea. Okay? Because this is what this is saying. Associate each point in X with each one of these outcomes that is one of these red bars. Okay? Well, this is the other point of view. Now I want to focus on the last kind of transformation. Okay? The last kind of transformation will be slightly different from this, because so far we only considered multiplications. You either multiply the outputs or you multiply the arguments. Well, now let's consider summing. Let's sum something to the inputs. Let's sum a constant. So instead of sine constant times x, let's consider theta plus constant. Okay? Let me just call this, instead of theta, let's call it alpha, to make it easier to understand. What are the functions involved in here? Well, it's not g is different now, it's g of alpha, and alpha is g of alpha is alpha plus constant, and the f remains the same, okay? This is a polynomial of degree 1. Recall that a polynomial of degree 1 in alpha must be a times alpha plus b. In this case, b is a constant and a is 1. So this is a line. This represents a line with slope 1 and y-axis intersection at constant, the number that you choose. I want to give a good name to our constant, so let's call this phi, the phi constant, the Greek letter phi. Okay? And let's make the composition to give this function. So the composition is f of g of alpha must be sine of alpha plus something. Okay? Is this good? Now let's proceed in a similar way. Okay? We want to compare the graph for this thing with this thing. We already know the analytic part of the transform is just add. Now let's see the graph before and after. Okay? For that we need to ask our criminals and get information and then piece together the information. Okay? And this is not writing well. Let me see this one. Periodicity. What's the periodicity of this function? Well, notice that alpha plus phi is an angle, right? Like theta was. You see? This is our old theta here. Became alpha plus constant. So anything that we add to alpha plus phi leaves the function when you add the period, a full perimeter of the circle, you get the same value what you used to have. So sine of alpha plus phi plus n times 2 pi leaves the thing unchanged, that is equal to sine alpha plus phi. This is theta and this is theta. Okay? So this transformation doesn't affect the period. Okay. Maximum minimum. Maximum minimum. Well, the maximum minimum, this is still the sign, right? And so the maximum is still 1 or minus 1. However, on the horizontal axis is different, right? Let's write the conditions that determine this, where on the horizontal axis we find this maximum minimum. So sine of theta max, the position on the horizontal axis where I find the maximum, plus phi must be 1. So whatever phi max is, a name that I gave to this value, well, when I put it here, it must give this number, okay? Phi is a number that you choose, an angle. Sine alpha mean plus phi must be when the sign takes minimum, so it's minus 1, or sine of alpha 0 plus phi must be 0. Now we solve this by comparing this with this. And the conclusion that we get is that alpha max plus phi must be pi over 2, or in other words, alpha max must be pi over 2 minus phi. Compare this with this, and we realize that alpha min must be 3 pi divided by 2 minus phi. And finally, this must be either 0 or pi, and so alpha 0 must either is 0 or alpha 0 is pi minus phi. Okay? This is the first conclusion that we get. Okay? For this thing. Now, let's see the symmetry. I'm sorry, the symmetry. The symmetry or anti-symmetry, does it exist? No, it doesn't exist, right? Because if you add anything here, you broke the symmetry, right? So there is no anti-symmetry in this case. So what happens on the positive side of the theta axis, the alpha axis, is not the same that occurs on the negative side. Okay? But still, with this kind of information and knowing this, we can start making progress. Okay? So let's use what we have so far and do the best we can. Okay? So here again is our function, and this is failing again. Let me just okay, I have to use another color. I use the black. Okay. We mark the important points, the first to pi, and then pi, and then pi divided by 2, 3 pi divided by 2, right? Here, minus pi over 2, minus pi, minus 3 pi divided by 2, minus 2 pi. And now we proceed, you mark here the 1, this is 0, this is for the sign, of course. Again, we need a reference, the sign is always a reference. And then we fill the gaps. Okay? Easy it is. Now this is negative, 0, positive, and 0. This is a bit above. And we run like this. Okay? This is the sign. So this is axis is theta. Okay? Now, what I want to do is to draw the transformed function, the composite one. Notice that it is a function of alpha. So I would need another axis called alpha and draw the graph here, above this thing, above these inputs. But because I want to compare before and after, I'm going to superimpose the two graphs. So I'm going to bring this horizontal axis and put on top of this one. And so the values of theta and alpha are going to coincide. And whether I'm talking about theta or alpha depends upon whether I'm talking about the graph of the sine or the graph of the composite function. Okay? Now let's start by marking here the important points. Let's choose a good phi. What is a good phi? A good phi, let me think. Maybe let's choose pi. Pi is a good value. Let's choose phi equals pi. Right? Let's see what happens. So the alpha max, now it's pi over 2 minus pi, which is minus pi over 2. So above this point, we mark the maximum, this height. See? Notice, compare. The old maximum is here. The new maximum is here. The old minimum is here. The new minimum is at 3 pi divided by 2 minus pi. Now you just go pi from here. I'm sorry. From here to here, this is the minimum now. Here, above pi over 2. Right? 3 pi divided by 2 minus pi is pi over 2. If you don't see it immediately, let me just draw you here a picture. 3 pi over 2 is the measurement of this angle from here to here, right? Well, pi is f, so if you go 3 pi over 2 minus f, you land here, but this angle is pi over 2. Here it is. Let's move on. The zeros. I'm sorry, this is... No, this is minus phi, I'm sorry. Of course, yes, it has to be minus phi. Okay, so at minus phi, that is at minus pi, you get a 0. Let's put in green. And at pi minus phi, that is at 0, you have 0 again. And now let's see the period. The period is again is 2 pi. And so let's copy these values from minus pi to pi. Well, distance is 2 pi, so this value must be 0, like this one. This is minus pi over 2, this is 3 pi over 2. The distance is 2 pi, and so this is 1. For me, this is 0, this is 2 pi, so this must be 0. And let's keep on going. From 0 and minus 2 pi, this is 0 again. And here, let me see, this is minus 1, this is minus 1 as well here, right? This distance is 2 pi. I'm just comparing to pi all the time. You see, because I know that the function must repeat. Okay, so I use the ones that are already marked to get the others, but the missing ones. And now let's fill the gaps. Well, but we already know how to fill the gaps. The behavior is something like this. Like this. This should be the 0. And like this. And now like this. Okay? Can you see? The green curve is our f of g, our transform function when phi is pi. Notice what happened. It just shifted to the other side, right? Like this. So you add to the argument an angle and the thing shifts to the left. That's actually counterintuitive, because you would think that if you add something, it gets more positive, so it must move into a positive direction, right? But no, it happens the other way. You add and you move to the other side. By how much? By pi. So the old one, the old maximum, moves to the minus pi before, right? At minus pi over 2, and all the zeros as well. So this is a rigid shift. Okay? Well, this is all good. This is the way to go to make this picture, like we did before. But now, let's... by the way, before I move on, what do you think it happens when phi is now negative? It's a homework, okay? You can, again, use these formulas and do yourself the pictures. I think you know what's going to happen when instead of pi you put here minus pi. Okay? It's an exercise, a good exercise, because I want to move on to the other point of view. Okay? The other point of view is the assembly line point of view, just like we did for the previous case. We want to compare the following assembly lines. We start with alpha. You transformed alpha with the function phi plus into phi plus alpha. This first part. First you act with g, and then you act this with a sign. And you get the number sine of phi plus alpha. Okay? The second assembly line is smaller. It's just old sine. So it's theta, and it moves with a sign, and you get the value sine of theta. Okay? Now we want to compare what this thing is actually doing, but in order to do that, we need to understand the parts that compose these functions. So it's this function, the g function, and the f function, which is f as well here. Okay? So let's analyze the pieces and then join the thing. Okay? So let me just use this. Okay, let me see if I still have. Okay, it's not good. This is not good. Let me just use it green. Okay, this is a line with slope 1 with phi as the y-axis intersection. This is alpha, and it's something like this. Okay, so this is phi. The distance from here to here is phi. Okay, this is our g function here. Now I know that this first part, well, if you give a value, it transforms it to another value. If I choose a value, it gives me another value. Fine. If I give a set of values, for example, like a belonging from 0 and pi divided by 2, then let's mark here (0 and pi over 2). This is our set A here, and if phi is pi, then you are going to transform this thing into another set. Let me just copy it. I need to extend this thing, so it starts here and it lands here. Okay, this set, you see, but it starts with A, and you get what? You get a plus phi. You see, a plus phi is just a shorthand notation for a set. This is a set. A set that comes as a result of summing to every value of a phi, in this case pi, okay? Because phi is pi, right? So let me write it that phi is pi in this case. You can see it here, okay? This is a plus, plus pi. This is a. So this first part is transforming this set into this set. Notice they measure the same. There is no extension in this case, but this is displaced, as I'm about to draw on the horizontal axis. Let's draw horizontal axis. Put it straight. This is the 0. The whole set is from 0 up to pi over 2, right? This is pi, so this is the 0 from pi over 2. And now the consequence of this part of the assembly line of this transformation of acting with G is to shift this by pi. So it starts at pi and goes until 2 pi, right? So this is a plus pi. Well, this is a, right? So you turn this into this, right? This is the consequence of this first part. Now let's analyze the second part. We already saw it before. Let me just focus on the y-axis, on the positive side, and it's something like this. Okay? And now, let's see. Let's focus on this assembly line first, which is associates values in theta in A to sine of A. You already saw this. This is A, set A. From 0, this is A, until the max. And the values that you get are these ones. Okay? So all these heights from 0 to 1 are the values that this function associates with A. So this set of values is associated with these heights here. This is what the function does, associates elements of one set with another set. And you see this graphically here. Is one set, the bars is another set. Okay. Now, the other assembly line does something first. Before evaluating the sign, it first transforms. It transforms A into pi plus A. So let me draw pi plus A. Okay? So you get this. I'm sorry. I must be making some mistake here. Of course. There is a mistake here. Okay. Because it starts at pi. This is not good. I'm noticing now. Okay? Because it's 0 up to pi over 2, and the other one starts at here and goes up to here. So it starts at pi and goes up to pi plus pi over 2, right? So this part here is now the A plus pi, right? So it doesn't start here. It starts here. From pi until pi over 2 plus pi. So this thing here is this, right? A plus pi. The set of values is this. So this is the first part. You transform A into this by this, and secondly, you evaluate the sign on the set A plus phi. You evaluate, like we see here, over this set, the values. Okay? From 0 to -1. Okay? Now the key point is that while this assembly line associates to the A values here the set of outputs here in blue, these bars, from 0 to 1, this is what this does. This, on the other hand, will associate the alpha values in A not to the blue ones, but to the red ones. You see? The outputs because the red ones are sign evaluated at the new window, a plus phi, the new window, and the evaluation is here, okay? So the idea is that each one of these points in A must now be associated with these bars. But graphically, what's the consequence of this? What's the consequence? The consequence is that when you have to draw now the composite function, over A must be these bars, the outputs. That's what we draw. When you draw a graph, what's above the x-axis, or the horizontal axis, are the outputs. But if this function associates with this set of values these, then these must be above these. Okay? But what that amounts to, shift this thing to this side. You put this thing here. Okay? It does like this, right? Is it okay? This is what happens here. Okay? You have to shift in this direction by pi. Okay? You shift in this direction by pi, so that the A values of A could be any set. It doesn't have to be 0 and to pi over 2. It could be any set. You have to always shift the thing and push it by pi. Okay, what you see here. You have to bring the evaluation on the new window, which is pi later, and bring the evaluation which happens at pi later to the current position A. Because this is what it does. It associates with A the outputs evaluated at the new window. Okay? Well, this is the reasoning behind all this, the justification of these kind of transformations. I really hope that you go through this step by step. You have also the notes in the description as well as exercises for you to train this kind of stuff. And I wish you good work and see you next time. Goodbye.